Okay, good. I'm gonna start. Are you ready?
Is there anything important in the chat?
Hang on. No, it's just diagnosing that people can hear.
Okay.
And you can still hear people in the chat. Can somebody just give me a yes? Okay, awesome. Wonderful.
Yeah, good idea. Thank you.
Hang on. Too much?
No, that's too many photons.
No, I think the only control I have is this here.
Yeah, but that looks better.
Yeah, I was just flickering it first. Okay.
Good.
Yeah. Good to go? All right. Hi, everybody. Welcome to the first colloquium of the fall semester. It is really my great pleasure to introduce Dr. Jennifer Lotz to kick off our colloquium series this semester. Jennifer and I have known each other for quite some time. We were office mates together in the WAR Lab, which is the U.S. National Optical Infrared Laboratory for Astronomy. Dr. Lotz got her undergraduate degree at Bryn Mawr and then went to Johns Hopkins for her PhD. And she was kind of doing this in somewhat of like the first decade of Hubble Space Telescope operations. So it was there when Hubble Space Telescope was doing a lot of its original deep field work. She then moved to a postdoctoral research position at Santa Cruz, UC Santa Cruz, and then the Goldberg Fellowship at NOIR Lab, which was then called the National Optical Astronomy Observatory. We both had that fellowship. That's where we met. And so we've kind of been close to touch, both the scientific colleagues and friends ever since. After she was in Tucson, she then moved to Baltimore to the Space Telescope Science Institute, which is the institute that runs, among other things, the Hubble Space Telescope. And then she was given the director position at the National Gemini Observatory, which is essentially the International Gemini Observatory, which is two 8-meter class telescopes, one in Hawaii, one in Chile, and they are the premier public access US observatories that anybody in the US and indeed the world can apply to. So she was the director there for, I think, 5 years, and then got the chance to become the director of Space Telescope Science Institute. So kind of going back between Tucson and Baltimore. You've been there now for a little over a year.
Year and a half.
And a year and a half, and Space Telescope Science Institute, it's not an understatement to say that it runs the most powerful and influential observatories on or above the planet. So both in charge of the Hubble Space Telescope and the James Webb Space Telescope and the future Nancy Grace Roman Space Telescope. So it's really fantastic that we can have Dr. Lotz here. I hope that some of you had the chance to talk to her. We're also really happy to have in the audience guests from Senator Moran's office and Senator Marshall's office. So it's really wonderful they could come out and hear Dr. Lotz's talk. After the talk, we're going to have 10 minutes or so for students to ask her questions when all the faculty leave. So till about 12:10. You're going to see me get up and leave at some point early. It's not because I don't like to talk. It's just I have to teach at the 4th floor of Wesco at 12 o'clock. So I'll be leaving early, but not because. What?
You're Catholic.
I've been doing it all day, up and down. All right.
All right.
Cool. So without further ado.
Okay. Thank you. Thank you, Greg, for that great introduction. Thank you to Greg and Ian and everyone for having me here. Hopefully, I don't know if there's feedback, if everybody online can hear me okay, but you need the mic up.
Or just put it in the middle.
Well, not sure. I know. PhD, can you figure out a mic?
It's not there. It's good online, so you're good.
Okay, all right. I'll keep going and I'll talk loud in the room. Thank you, Greg, for not sharing any embarrassing stories from our postdoc days. I appreciate that. Greg and I have known each other for a long time. So I'm going to give a presentation that's probably a little different from the typical colloquium that you hear about. I have the tremendous privilege of being the director of the Space Telescope Science Institute and helping to make science happen with these amazing NASA flagship missions. So I'm going to give kind of a whirlwind status report of these three major astrophysics missions, and then talk a little bit about the future, both the good and the bad, right? But for all the young folks in the room, I want you to appreciate just what an incredible time we live in for studying the universe. We are able to ask and try to answer some truly profound questions. When did the first stars and galaxies form in the universe? We are now seeing with Webb the very first galaxies just a few 100 million years after the Big Bang. What is the nature of the universe? We know that the universe is made up of dark matter and dark energy, but we don't know a whole lot about those things. But the new telescopes that are coming online now will really help us understand our picture in the universe. What is the nature of the universe and how does it evolve over time? What are our cosmic origins? How did our galaxy form? How did our sun form? How did our solar system form? How did our planet Earth form? And can we see other systems like that as we look out across the universe? And then this last question, is there life on other planets, is moving out of the realm of science fiction. I'm a huge Star Trek fan. I love science fiction, but this has become a real scientific study. Like, what are the signatures of life on other planets? What does it take for our technology to be able to detect that, really? And I'll say a little bit about that at the end. So how did we get here? How did we get so lucky to be able to ask and answer, or try to answer those questions? So in the United States, the US astronomy community every 10 years or so gets together with the national academies, and they put together a report called the Decadal Survey. And this is a set of recommendations both to NASA and to the NSF on what should be the highest priority projects for the decade. So, in the 70s, the highest priority project was Hubble. Then came Chandra, the X-ray Space Telescope, which is still in operations. Then the Spitzer Infrared Telescope. Then in 2000, the James Webb Space Telescope was the top recommendation. Following that, in 2010, the decadal was the Roman Space Telescope. Then it was called WFIRST, and we are just a year and a half away from launching that telescope. And the last Astro 2020 Decadal Survey recommended something that we're now calling the Habitable Worlds Observatory as the next major flagship big project for NASA astrophysics. So the Space Telescope Science Institute has been really fortunate to be part of this from the beginning. What you can't read under there says that Space Telescope has acted as the bridge between NASA and NASA's astrophysics flagship missions and the broader scientific community. So in the 70s, when they were looking for, how are we going to operate this not yet named Space Telescope, this report from the National Research Council determined that the Space Telescope Science Institute was needed to provide the long-term guidance and support for the scientific effort, to provide a mechanism for engaging the participation of astronomers throughout the world, and to provide the means for dissemination and utilization of data derived from the Space Telescope. So we have, over the last 4 decades, really tried to live up to that, to put science first in everything that we do, in partnership with NASA. And, we do that through supporting our mission. So I'm glad they didn't call us the Hubble Space Telescope Science Institute, because now, there are multiple space telescopes. We support Hubble, which is, a 2-meter telescope that does ultraviolet, visible, and near-infrared imaging and spectroscopy. It's in low Earth orbit, so it's only about 300 miles up. And there was a time when we used to send astronauts up to fix it in space. And I think you have one of those astronauts on your faculty. So, huge thank you to the people who risked their lives to make that possible. The James Webb Space Telescope launched just a couple years ago. It's a very different beast. It's much bigger, 6.5 meters. We had to fold it up to sit at the top of a rocket. It's got 17 different instrument modes, and it's really designed to do incredibly sensitive observations in the infrared. It's got a 20-year lifetime, but it's not planned to be serviced. We're not going to be sending astronauts out to L2 where it lives, and it was not designed to do robotic servicing. Next up is the Roman Space Telescope. That is a different thing altogether. Similar, sort of sitting in between Hubble and Webb in its wavelength regime in the visible and infrared. The main instrument on that is a wide field imager. That's going to be able to do surveys of the sky. So Hubble and Webb are kind of point and shoot cameras. Roman takes big field of view and it can slew really fast. So it's going to have a survey speed that's 1,000 times that of Hubble. There's another instrument flying on Roman, which is called a coronagraph. And I'm going to say more about that. But it's really an incredible technology testbed for trying to push our technological capabilities for detecting and directly observing exoplanets, so planets around other stars. It's due to launch no later than May of 2027, but as I'll tell you, it's actually ahead of schedule, and so it may be coming up here really soon. And then, of course, all of these telescopes create vast amounts of data. We host that data in the Mikulski Archive for Space Telescopes. So that's the data from Hubble, the data from Webb. We will host the data from Roman, but we also host data from another number of NASA missions, as well as some data sets from the ground. So we are the Science Operations Center for Hubble and Webb, and that's a really important part of making science possible. What does that mean to be the Science Operations Center? Well, if you're writing a proposal to use the Hubble Space Telescope or the Webb Space Telescope, it comes to the Institute. We help convene the selection committees and do that peer evaluation. Those programs that are selected then get fed back to our team. We work with the team to make sure that the right commands to the telescope are in place and actually build out that year-long schedule. We then ingest the data when it comes back off the telescope. We do the calibration, we do the data processing, and then we put that into a public archive so everyone can download that data, including the people who originally proposed to use that data. We support the grants that are used to analyze that data, and then we also do support public outreach. So those amazing images and press stories that you hear about Webb and Hubble come out of the Space Telescope Science Institute in collaboration with our partners at NASA. So I'm going to talk a little bit about Hubble, the status of Hubble. Hubble just celebrated its 35th birthday, which is incredible. And the amazing thing is that Hubble really is even more scientifically productive than it was a decade ago, which is pretty amazing. So last year was a record number of publications, over 1,000 publications. It is one of the most scientifically productive instruments ever made. It's got 21,000 papers, over 1 million citations to date. You know, the demand for Hubble is still 5 to 1. So for every proposal that gets submitted, only one gets approved. And we're finding, even though James Webb is now flying, those telescopes are very synergistic. And so a high fraction of the new James Webb papers also refer to Hubble data. This is even more impressive when you realize that Hubble's funding did not dramatically increase over that period of time. It actually stayed flat. And so with inflation, you know, we've been doing more with less for over a decade. You might wonder, okay, it's 35 years old. Is it coming down anytime soon? You know, Hubble is expected to be able to do good science for another decade or so. We expect it to live into the 2030s. So this plot here is a plot of the reliability of Hubble's main instruments. WISC3 and COS are newer, so they're very solid. STS and ACS are older. I think Steve actually installed STS for us. But there's a high chance that those will be operational. Really, the limiting lifetime that we expect is Hubble's orbital decay. We recalculate that decay rate on a regular cadence. And the current expectation is that Hubble will re-enter the atmosphere around 2033. There is a very small probability that it will re-enter in the next 5 years. You may have also heard that we needed to change the way we operate Hubble. So Hubble has what's called gyroscopes that help us maneuver and point it. Originally, there were 6. We're down to 2 working gyroscopes. And last year, we made the decision to shift to operating Hubble with a single gyroscope, which is a pretty amazing technological feat in itself. And we were able to do that actually with no impact on the quality of the data that comes out. We're not as flexible in where we can point on the sky, but the data that's coming out is just as good as it has ever been. So I talked about Hubble being complementary to Webb. Hubble strength is in the blue and in the ultraviolet. So this image here, you can see Hubble imaging of a star-forming region. You see bright blue stars and clouds of gas. Sorry, that was on the left, and on the right, you can see the image taken with Webb, in which these areas of darkness, which are dust clouds, are glowing up and lighting up in Webb. So these two views of the universe together really give us a complete understanding of what's happening in the star-forming region. One of Hubble's strengths has been to provide real-time monitoring of objects in our solar system. So let me click the movie here. Hopefully that plays for everyone. I don't know if everybody remembers the DART mission. So this was a mission to actually see if we could hit an asteroid and move it. That DART mission was observed both with Hubble and Webb simultaneously. Hubble came back and took a look at that asteroid, and you probably can't see it in the room, but maybe online. There are a whole bunch of little circles here from this Hubble image. Those are the boulders that flew off of that asteroid. And actually, that's where the momentum went when you hit it, it flew off in this debris. We monitor the solar system regularly. We can see what the weather is on Mars, watch the polar ice caps grow and shrink, watch the clouds go by. And then most recently, Hubble observed this really interesting interstellar visitor, 3I Atlas. It's not a spaceship, we're pretty sure. It's moving, but it's really interesting. It's a comet that's moving incredibly fast through our solar system. And Hubble's, because of its high spatial resolution, is able to determine the size of that comet. And there's a lot more programs, both with Hubble and Webb, to track that interstellar comet. One of the things that Hubble can do now that it couldn't do initially was like long baseline observations. So this is an amazing movie of a binary star system, a red giant, white dwarf. It's ejecting a lot of material. And I don't know if you can see it, the dates are kind of in the lower corner there. Over multiple years, we can see that material flow out and really get to understand what's the interaction of these binary star systems and the surrounding interstellar medium. One of my favorite results from Hubble in the past year was this archival study of the center of a globular cluster called Omega Sun. So Omega Sun is a dense star field. It's actually a calibration field. Hubble goes back to this field all the time just to calibrate its data. And that's sitting in the public archive. We now have decades of observations of this star cluster. And what this group did is they took the public data set, the well-calibrated public data set, and they tracked the motions of stars in the center of this globular cluster and saw that 7 of them were moving around and moving so fast that there had to be a black hole, an invisible black hole, sitting in the center of that cluster. And that's the kind of science that is possible with decades of consistent, high-quality public data. So I'm going to move on to Webb. That's just the tip of the iceberg of science with Hubble. But this is the photo of Webb as we were saying goodbye to it after its launch just a few years ago. Webb has been amazing. So I work in the field of high redshift galaxies. It's been mind-blowing. One of the key messages, after a long time building and working on Webb, a lot of work and effort went from thousands of people across the US into making this happen. It's really performing better than expected. So it's providing an order of magnitude better inference sensitivity relative to previous capabilities. That's enabling all kinds of science. It is incredibly stable. So it's got these segmented mirrors. We thought we would have to work to align those mirrors every couple of weeks. We only have to align those mirrors every couple of months, every 6 months. And so that's what this plot on the bottom here is, what the distortion is in the wavefront error is over time. We expect that it has over 20 years of propellant left. And so if we're careful with this telescope, it should last for decades, which means the year-over-year cost of that will be, make it worth that investment. And in the last couple of years, we've done a lot of work to make the science operations of Hubble a lot better, improving the calibration, the pipeline, and the guide star catalogs. So one of the challenges is James Webb is so sensitive that the catalogs we had for stars in the sky were just not deep enough, particularly when we looked at dense fields. So we'd get confused. And now we have all new catalogs of stars and are much better, better able to point Webb where we think it should be pointed. So it was really built to be a machine of studying the very distant universe, and it is truly transforming the studies of the first galaxies. So we have press release after press release. We're finding galaxies and black holes just a few 100 million years after the Big Bang. So we see that galaxies are brighter than we expected. We're seeing that there are more of them. We're seeing that there's a lot of activity in them, all kind of blowing our minds about how star formation in the first galaxies form. The thing that is hard to capture often in a press release is that this is coming from the spectra. So when Hubble would have a little red dot and we'd get really excited about it, now we have this ability to really look at the chemical composition and the ionization and the energies associated with these galaxies. So we can see that there's rapidly moving gas in the centers, which indicates a black hole. We can get precise distances of redshifts by looking at the spectral features, and we can look at other signatures. Is there gas? Are there gas? What's the ionization state of that gas? So it's got everybody thinking about what is the early state of the universe. Really, really exciting. It's doing a lot more than just high redshift galaxy studies. This is a result related to cosmology coming out of Adam Rees's group, where they went back and looked at nearby galaxies, looking for this special class of stars called Cepheids. So Cepheids are an important distance indicator, the first rung on the ladder for understanding cosmology. You can see the difference between the spatial resolution of Webb versus Hubble, resulting in much more precise measurement of the distances to these galaxies, and really confirming actually that there is a true difference between the Hubble constant in the local universe and the Hubble constant in the distant universe. This is called the Hubble tension. We do not know what this means. This means that our understanding of how the fundamental parameters of the universe evolves is an open question. JWST is unveiling the details of amazing dusty star formation in nearby galaxies. This is a montage of Hubble blue in the bottom and James Webb in the top. We've surveyed many, many other galaxies and really being able to see through that dust and understand how star formation in galaxies that are a lot like our own Milky Way proceed. If we zoom in on one of those star forming regions in our own galaxy, again, Webb is unveiling something that we didn't see before. So this is an image of the iconic pillars of creation. You can see Webb is revealing the dusty columns there. If you can see at the very tops of those columns, you can see little red dots, which are protostars forming in those star forming regions. And then we can follow up with spectra and understand the chemical composition of those protostars. And we can see complex organic molecules. And that's telling us a little bit about what the early conditions of probably the proto-solar systems around those stars are. So it's giving us an insight into maybe these stars are not that different from how our star and our solar system form. This was an interesting and fun thing from last year. JWST is turning out to actually be an important facility for planetary defense, which is, I think, not something we originally thought of. If you might remember last year, people were a little nervous. There was a asteroid that was detected that had a non-zero chance of hitting Earth. It was like 1%. It's no longer likely to hit Earth. It might hit the moon. But Webb was one of the few facilities that could really observe this as it was moving away from us, and get the size. Really, with its spatial resolution and sensitivity, it could figure out how big was this asteroid. And so they determined that it's actually the size of a 15-story building. And so we'll be tracking this as it comes back around and seeing if it's likely to hit the moon, which would be interesting, but it's a little too close for comfort, I think. All right. One that's really recent, just out in the last month. JWST is revolutionizing our study of exoplanets. So exoplanets are planets around stars that are not our own sun. This group looked at our nearest neighbor, Alpha Centauri, which is actually a triple system, Alpha Centauri A, Alpha Centauri B, and there's a dwarf star in there. They use this technique called coronography. So Alpha Centauri A is where that orange star is. We blocked it out. We used the mid-infrared coronagraph to look to see what was around it. And we found a Jupiter mass planet around our nearest neighbor. This is amazing. We now know that the nearest star to us has planets, at least one planet that's not that different from our own Jupiter. So this was really, really exciting. This is just one way to study exoplanets with James Webb. We are starting a major program. We've actually kicked it off this year called the Rocky Worlds, DD stands for Director's Discretionary Program. And this is going to use Hubble and Webb together to try to answer the question of, are there atmospheres on other rocky planets? So this is actually a picture of Earth. This little blue bit is our atmosphere. It's not very big, but we can, with Webb, detect the signatures of an atmosphere by looking really closely as planets move in front and behind of their host star. So this study is going to survey about 15 or 20 rocky exoplanets that live around a particular kind of star called an M dwarf to see if they have atmospheres, right? If it's possible. And we think atmospheres are a critical component of whether or not a planet can host life. That's going to involve 500 hours of JWST mid-infrared time. It's also going to include 250 orbits of Hubble time in the ultraviolet. So M dwarfs are the most common kind of star in the universe, but they're very active. They actually, they're called angry red stars because they often eject X-rays and ultraviolet light, which can make atmospheres evaporate, right? And make life on planets really difficult. And so those ultraviolet observations with Hubble will be really important for understanding if that's possible. So we're going to use this to try to map out what's called the cosmic shoreline, understand when planets do have atmospheres and when they don't, what kind of properties of the stars are likely to result in atmospheres around rocky planets. And this is a really important stepping stone for understanding if life is possible on other planets. All right, so all of this is to say that JWST is performing incredibly well, both in terms of its operations as a telescope and scientifically. We think it's got a more than 20-year lifetime. There have been 1,200 papers at least published so far, over 750 in 2027. I think 2025 will be the year that it beats Hubble. And we're seeing that the scientific discovery cycle is accelerating. So the first year or two of Webb was just like, oh, wow, right? People were like, what does this mean? And now we're taking, the things that we discovered and learned in the first year or two and turning that into another set of questions and observations. And we expect that cycle of scientific discovery will continue as new facilities come online, like the Roman Space Telescope. It is really difficult and competitive to get time on James Webb. We saw last year over 2,400 proposals for James Webb. That means there's a 9-in-1 chance of getting a successful program through. And we're expecting that demand will continue to increase, especially given the experience we've had in the early days of Hubble and another incredible facility, ALMA, which is here on the ground. We've also seen that James Webb is now a household name, right? It's got a worldwide impact on public imagination. We weren't sure that it could displace or, counter Hubble, but I think people now appreciate really what Webb has to bring. And that that worldwide impact of the stories and the discoveries coming out of Webb, they're a really clear demonstration of the United States leadership and NASA's leadership in space and in science. So as director, I feel like we have to continue this, right? I've got 20 years. I want to make the most of those 20 years. And unfortunately, we're a little worried about what's going to happen, whether we're going to be able to continue to support at the level that we have been, given budget pressures at NASA. All right, let me talk about Roman for a minute here. What am I doing on time? Okay, so Roman is on track to launch potentially as early as September 2026, so a little bit more than a year. They're planning towards October, but they're just putting their foot on the gas. Let's get this telescope done. And it's, you know, it's almost all together. So this photo on the left is what's called the outer barrel assembly. So that's the outer part of the telescope. This photo on the far right is what's called SCIPA, and it's being lowered into a massive vacuum tank at Goddard Space Flight Center. That's all the science instruments and the actual telescope in one package. It's going currently through a whole series of tests, trying to make sure that it's ready for launch. And it is, you know, planned to be launched out of Florida, Cape Canaveral, on a SpaceX Falcon 9 rocket. I'm going to say a word about the coronagraph as the technology demonstrator and then move on to the surveys. So, you know, I showed you some pictures of coronagraphs taken with Webb. Roman coronagraph is really designed to be the next step up. It's being built out of JPL. It's going to be the first space-based coronagraph that's going to have active wavefront control. So it's going to actively try to mitigate any distortions coming out of the telescope. Webb is able to see 1 photon out of every million, detect things at that contrast ratio of 10 to the minus 6. We expect Roman to be at least a factor of 10 better than that. And actually our initial tests, I don't want to promise anything and I don't work on this, well outperform that. So it may be a factor of 50 or more better than the capabilities we have on Webb. And so this is designed to be a technology demonstrator. Can we do active control of coronagraphs in space? Can we push another order of magnitude or two down in our ability to see very, very faint things next to bright things? All right, the main thing for Roman though is the surveys using this wide field instrument. So here this slide is comparing what is possible with Roman versus Hubble and Webb now. So you can see, you know, Roman's this massive field of view. You can see the field of view of Webb and the field of view of Hubble. Hubble and Webb are designed to be point and shoot. Let's look at cool objects all over the sky with a whole bunch of different instruments and tools. Roman is let's survey the whole sky, right? So what Hubble would do in 1,000 years, Roman's going to be able to look at in about 10 months. It's about the same size mirror as Hubble, so the quality of the images will be similar. Now, Hubble still has a role to play because it goes much further into the ultraviolet than Roman. Webb goes much further into the infrared. So Roman's kind of sitting in that sweet spot of overlap. And I think there's going to be a lot of synergistic science. What you can't see under that little box is the other thing about Roman is we have to, because of the science requirements to do cosmology, we have to push the calibrations to an order of magnitude better precision, which is another technical challenge of how do we get better measurements at that level. So this is a slide that shows what the core surveys are going to be, and I'll walk through each of these. There are 3 surveys that are now defined and planned. You can take a look at what those are. One of the core drivers for Roman is to map the universe to earlier epochs than any other observatory, and really understand that evolution of the equations of state that really govern our universe. Understanding how dark energy evolves, understanding how dark matter evolves. So it's quite complementary in what's being done on the ground with the Rubin Space Telescope and what the Europeans have done with Euclid. So it's not going to be as wide of, you know, survey all the sky. Rubin is going to survey most of the sky. It's going to do it at visible wavelengths. It'll be focused on the lower redshift or the more nearby universe. Roman is going to go deeper, and it's going to be able to see the evolution of these properties out to earlier times, which I think is an important point for understanding how dark energy and dark matter have evolved over the history of the universe. So one of the ways it's going to do that is with the High Latitude Wide Area Survey. It's going to use a number of ways to do precise measurements of the cosmic expansion and growth of cosmic structure. A technique called weak gravitational lensing, which means it has to get very precise shape measurements of 600 million galaxies. It's going to do galaxy clustering. There's a low resolution spectrograph on Roman, so we'll be able to do what's called baryon acoustic oscillations, which is another technique, as well as redshift space distortions. If any of you are Hubble aficionados, you might be familiar with this galaxy program called Cosmos. So Cosmos is one of the widest area surveys ever done with Hubble, and James Webb is following up on that. That is this tiny little white dot here. That's one of the biggest surveys ever done with Hubble versus what the area of this wide latitude, wide area survey with Roman will be. It's just gonna, but the same quality of data is just gonna blow that out of the water. Another important tool for measuring, the expansion of the universe is looking for a particular kind of supernova type 1a. This is another standard candle. So to find supernova, you have to do a time domain survey. You have to see it was there, it's not there, right? So you have to go back to the same place in the sky. So there's going to be a high latitude time domain survey with a 5-day cadence. And that's going to really push, yet another technique for understanding cosmology out to high distances. And then last but not least is this, another science case is looking at the center of our galaxy, the galactic bulge time domain survey. And that's really designed to do something quite different. So looking at small fluctuations in the brightnesses of stars, you can use a technique called microlensing. So when an object passes in front of a star, the gravitational lensing effects will slightly brighten that star. And you can use that to find free-floating black holes, but you can also use it to find exoplanets. And we think this will be really powerful for finding tens of thousands or hundreds of thousands of exoplanets. So this is a simulation of what the center of our galaxy might look like with Roman. There's a lot of stars there. It's very dense. It's going to be a challenge to reduce that data. But if we do, we think that Roman will help us determine the population distribution of planets in the habitable zone. So this is going to be sensitive to analogs of our outer solar system. So other studies from NASA telescopes like Kepler and TESS have focused in on search areas sort of close to the star, kind of at the orbits of Earth or closer in. This Roman microlensing survey will help us look for the outer planets. And this is going to help us fill in the demographics of what kind of exoplanets there are, provide a lot of interesting candidates, which you could imagine Webb and other telescopes will want to follow up on. What are we doing? Space Telescope is going to be the Science Operations Center for Roman. We're doing this in partnership with IPAC at Caltech. We're going to build on the shared infrastructure that we built for supporting Hubble and Webb. So we'll be planning and scheduling of all the observations. We'll be archiving that data. There's going to be a lot of it, so I'll talk about that in a second. We'll be calibrating and doing the data processing for these wide field images. We're going to help with the science commissioning for that instrument. So when it launches, making sure that things are working. The community engagement, telling the story of the science behind this survey, and the public outreach. And one of the things that I think is important to know is this can be a lot of data. You're not going to download this on your laptop. So we're building that infrastructure called the Roman Research Nexus. So here's to scale. well, how the Roman data compares to Hubble and Webb. So this is how much data is, it's kind of off the screen here, how much data is downloaded from Hubble and Webb, 2.7 gigabytes, 58 gigabytes, Roman, thousands of gigabytes per day. Over the 5-year survey of Roman, we're going to have 20 or probably more like 30 petabytes of data. So we are working at the Institute towards being able to put all this data on the cloud, having people be able to access that data, be able to run your own algorithms, trying to build in AI to the exploration of that data. It's just a different way of doing science, right? Rather than you get your data set and you worry about every little photon, now you've got hundreds of millions of galaxies, you know, you've got to search through that database to answer the question that you want to answer. While those core community surveys are built around specific science requirements, the plan is to have all of this data be public as soon as it's taken over the course of the survey, 5 years. And we're going to offer a call for proposals this fall. That the due date is planned to be in March of next year. And that call for proposals is for 2 things. One is for funding, so that you can use that survey data to support your own investigations, including understanding cosmology or exoplanets or all the as a galaxy evolution all the cool things you can do with those galaxy data sets. And there's also a limited opportunity to do your own observations. So these need to be big programs. There won't be that many of them, but up to 25% of the time on Roman will be available for guest investigator programs. And, you know, look this fall for a whole bunch of opportunities to learn more about this training, how to use the Roman Research Nexus. You know, now is the time to be thinking about what you want to do with Roman. Okay, so I've talked about the science, but I think it's important to think about how these flagship missions have really changed the way that we do astrophysics. So Hubble and Webb drive science, astrophysics, across the entire United States. We see broad interest in both telescopes in terms of the number of proposals that are submitted. So last cycle, cycle 32, there were 44 states that submitted Hubble programs. There are 47 states that submitted Webb programs in cycle 4. And we see where that money flows back out through grants, also going to a wide cross-section of the United States. So Hubble and Webb and NASA astrophysics is really lifting up the enterprise of understanding astronomy and doing science all across the United States. We, of course, support the rest of the world as well. They're not eligible to get NASA grant funding, but up to 30% of investigators are coming from ESA, Europe, and they were critical partners in building both Hubble and Webb. And if we look at who's publishing papers, there are over 62 different countries that publish papers and propose for data. And US is leading that, but Europe and China are not far behind. One of the things that we've done differently over the last few years is the way that we review these proposals. So now we have a process called dual anonymous. So people don't know who's reviewing the proposals, and now the people doing the reviewing don't know who submitted the proposals or what institutions they're from. And so one of the things that's done is really had people focus on the quality of the proposals themselves, the science. But a side effect of that means that new people are now getting their programs accepted. So we call that DAPR, D-A-R-P. We implemented that in cycle 26, and we saw a growth so that, you know, new PIs using Hubble is about 30%. Of course, in cycle 1 with JC, everybody was a new PI. But we're seeing, you know, still in cycle 3 and cycle 4, a high fraction of new people coming in with new ideas, being able to use these facilities. And this proposal review process has now been adopted by observatories around the world. A key piece of what we do is to be able to provide those public archives. So well-calibrated public archives really multiply the scientific return of these investments, as well as increasing access. So we find that 2/3 of Hubble publications use archival data. So about 1/3 just use, data that they propose for, and that's all they publish. 1/3 use data that's purely in the archive, no new data, and then 1/3 use both. They both combine old data with new data to do something new. We find that the papers that are published using archival data come from a much broader set of institutions. And so that's really important for opening up access. And 90% of the papers published using archival data don't actually have funding associated with it. Last but not least, these flagship missions inspire the nation and the world. I've got two plots here. This is a plot of, what impact different stories with Webb had over the year. So we saw a lot of interest in a wide variety of things. This image in the back is the front pages of newspapers around the world when the first Webb images were released. So it was a worldwide impact and interest. We find that 25% of Americans have seen an image in space. Some people think that's a low number. I think that's not a bad number. It could be more, it might be more. But this is a direct return to the taxpayers on what they were doing with their money. And people that have seen those images are more likely to support NASA and US space exploration. All right, let's see how much time I have. All right, I'll see if I'll speed it up a little bit. I'll just say a few words about the federal outlook. All of this is not possible without support from the public and support from Congress. I wanted to say, recognize that we have had support from a broad cross-section of people in Congress. This is my boss, Matt Mountain, recognizing Senator Moran's support for astronomy through some of the challenges we had with the James Webb Space Telescope. So we really appreciate being able to have champions in Congress to continue to do this work. Roman learned the lessons from Webb. So Roman is on time and on budget, and it's actually ahead of schedule, we think. I'm not good. This report last year from the Office of Inspector General said we're meeting our cost obligations on schedule to launch. And, I think NASA has been able to crack, at least in this example with astrophysics, being able to deliver on time and on budget. And we want to take those lessons learned and carry it to the next mission. The proposed budgets look a little worrying for me. The president's budget request cuts NASA astrophysics by 2/3. This is not done yet. The House and Senate are looking to restore most or all of NASA astrophysics. The impacts are broad, hitting missions. So I feel quite fortunate that some of these numbers were not zero for Hubble and Webb and Roman. But we'll have to see how the budget process plays out to know how much of this work we can continue into the coming years. And for those of you, 25 million for NASA science seems like, or NASA seems like a lot. It is a lot. 25 billion is a lot of money. But in the grand scheme of things, NASA is not a major contributor to either the overall national budget or even the discretionary budget. 0.36% of the US federal budget in 2024. All right, so let me end on a good note. What's next? Budgets aside, we want to move forward with the next flagship mission. This was the core recommendation coming out of Astro 2020. And the idea was to build a large aperture UV optical near-infrared space telescope that could perform transformative astrophysics, but really as a driving science case, be able to search for signs of life on an Earth-like planet around a sun-like star. That would be an incredible discovery for humanity. It takes a long time to do these kinds of things. We saw with Webb, it takes decades. So the time to start this seriously is now. This is a fun simulation of that coronography technique where you blocked out the star, what our solar system might look like if you were some distance away. And you can see those fuzzy little blue dots, hopefully, that are Venus and Earth right? So the goal is to try to image those, like directly image Earth. But that might not be enough. You can't, by just looking at that image, know the difference between wonderful Earth with all of our life on it and Venus, which is not a place you want to go visit, right? Um, so spectra will be the key to determining from the light from that little blue dot whether there's a possibility of life on there. People always ask me, how can you do this? I'm not an astrobiologist, so I'm not gonna be able to tell you the details. We have at least one example. You know, this is the spectrum of our planet, Earth, and there's some things in that spectrum. Ozone, methane from cows, right? Molecules being out of chemical equilibrium that can, at this point in time, we think can only be explained by the processes associated with life. And so the astrobiology is a growing field and one that's, you know, is really looking hard at this question. So to do that, that is an incredibly challenging but exciting technological lift. We'd have to build an ultra-stable telescope that can keep a telescope stable at the level of picometers. Right now, we can't measure stability at the level of picometers. So to build the capabilities to measure the, you know, measure at the level of picometers and then actually build a system that can be stable over an extended period of time at the level of picometers. I would say Webb has made progress on this. Roman seems to be also being, our initial test, very, very stable. Habitable Worlds would be the next step. We talked about ultra high contrast ratio, how Roman is a step, order of magnitude, maybe 2 orders of magnitude better than Webb. We need a similar step from Roman to be able to do this work with coronagraphy. We're talking about a big telescope, 6 to 8 meters, maybe bigger. We need a big rocket to fold it up and send it out on. And then we'd like it to be something kind of like Hubble, where we can go back, right? We don't have to, you know, it limits the risk. If we don't have to get every single thing perfectly right on the first try, if we can go back and replace and upgrade instruments and other key capabilities, one way to do that, we wouldn't necessarily need astronauts. We could send robots out. All right. So for the astronomers in the room, this is what we're thinking about in terms of the suite of instruments: a large telescope, high contrast imaging and imaging spectroscopy with a coronagraph, with that contrast ratio of 10 to the minus 10. We'd want a high resolution imager capable of imaging in the ultraviolet, visible, and near infrared. And we'd want a wide field spectrograph, a UV multi-object spectrograph, which would enable a lot of additional science. This is all TBD, of course. And if you build something like that, it doesn't just do study, it's not just capable of studying exoplanets or life on other planets. It's capable of answering a lot of other questions, pushing the discoveries we've made with Hubble and Webb to the next level. All right, this is my last slide. So a month ago, we had an amazing symposium in Washington, D.C. towards the Habitable Worlds Observatory. There have been committees of astronomers who've been thinking about the science cases. There have been committees of engineers who've been thinking about this technology. And this symposium was a chance to bring those folks together, talk about those ideas, and push forward with the next thing. So I encourage you to check out this conference. All of the talks are on YouTube. And in particular, if you're a scientist, you could go and look at this link here and look at those detailed science cases, see what's in there for you. You know, we're really just getting started. So to end here, you know, we are entering a truly amazing era for science and astrophysics with cosmology, exoplanets, time domain, star formation. And we're going to be at this time when Hubble and JWST are going to be operating all at once. Space Telescope is here to support you and to be that bridge. And NASA flagships are important, not just for those discoveries they make, but because they have a broad impact on the nation, the way that we do science, a role in public imagination as a demonstration of our leadership. And we'll have to see what happens with NASA budgets. I'm worried that this is going to be a risk to our ability to lead in the future. Thank you. Okay, so thank you very much, Dr. Lotz. We have some time for questions. My goodness. I want to make a point first, though. Can you go back to the slide where you show all the states and who's getting time? Yeah. So you guys, I hope everyone knows where Kansas is on the map. Okay. All of that comes from the 4 astronomers in this department. So that is all of it. Okay. So let's go to online first. Lena has raised her hand, so let's go to Lena.
Hi, can you hear me?
Yes. Yes.
Hi, this is Lena. Thank you, Dr. Lotz, for your amazing talk. I have a question. So at the beginning, you talked a bit about the synergy between JWST and HST, and now you're talking about Roman, and you kind of hinted at this, but what do you foresee would be the synergy between Roman and the pre-existing observatories?
Well, I'll say that it goes both ways. So right now we have opportunities for people to do preparatory science with Hubble and Webb. So initial explorations that will help them understand, what work they could be doing with Roman. One example is we have a Hubble survey right now of the galactic bulge. So that's going to help people design and do better with the Roman galactic bulge survey. I talked a little bit about Cosmos as a precursor to the high latitude wide area survey. But I think once Roman's launched, Roman is going to be amazing for lots of things. When you have, hundreds of millions of galaxies or, billions of stars, you're going to find some really interesting things in that sample. And you might want to go back and then do a really detailed study of a carefully selected sample with the other capabilities that are offered with Hubble and Webb. So I think there'll be a really, really good synergy there. Great. Any other questions online first? Okay, we have time for a couple questions in the room. Daniel.
Yes, thank you very much for your talk. It was very interesting, and thank you for coming here, and we are very happy. What do you think about the participation of all the countries on this, Roman? How is like the Europe and China, and how that plays into this conversation of the budget? Because I'm from the, I'm in nuclear physics, and this is very important in the discussions, the international component, and what other countries want to do.
Maybe I'll tell you a story,
Okay.
right? So we open observations to anyone in the world. Anyone can propose to use these telescopes. Anybody can download the data. One of the senior officials in Japan was amazed that, their faculty had won this very competitive JWST data. And he said how that really demonstrated the leadership and the generosity of the US. So I personally think that creates a really important culture of both collaboration and competition. Both are needed, right? We see that in building James Webb, we could bring in partners from Europe. If we build Habitable Worlds, we already have international partners that want to contribute to that. That helps us move further together. But having that healthy competition with different countries having their own space agencies or their own science programs also helps us do more. I think we've been incredibly lucky here in the US to have all these opportunities and all these facilities, and I hope we can continue that. Okay. Kai.
Hi, thank you again for the talk. This was amazing. So as you mentioned before, the observing area.
No, yeah, you guys watch out. There are like steps in this room. Don't love this.
The observing area with the Roman telescope, like you said, is significantly larger than anything we've had before, really. Do you see a lot of labs, do you see you guys taking a bit more of an interest in looking at labs that use machine learning algorithms or stuff that's specifically meant to process much larger amounts of data, since we're getting so much larger observing area?
I absolutely think this is a huge opportunity for machine learning. back when I got to do science, I used to do some machine learning techniques for analyzing images of galaxies. What we're trying to do at the Institute is to build the platform to make it possible, right? So make sure the data is accessible, that people can come to the data, bring their code, bring their algorithms, connect to whatever tools are available within Amazon Web Services, be able to do their own analysis, because your ideas are going to be better than whatever limited ideas we can come up with. And so I think this is, yes.
All right, so we're at the top of the hour, so we have one more question right here.
So you said that Roman and Hubble are about roughly the same size. And you said that we are going to be surveying dark matter and dark energy, correct? So if Roman and Hubble are the same size, what is the difference between them that makes it able to do that? And is there a possibility that we would be able to get a clear image of a black hole?
Oh, okay. That's a lot of questions.
Sorry.
So the main difference is the focal ratio, right? So the way that, the overall diameter of the mirrors is about the same size, but the way that the focal ratio for those two telescopes is quite different, right? And, look at your optics textbooks on that. So one is designed really to be a wide field of view. Maybe, interestingly, history of the Roman Space Telescope is it started off as a donation from the National Reconnaissance Office, where they used to look down, right? So and we repurposed it for looking up. Black holes, you can't, black holes by definition, you can't see directly, right? But you can see them in a couple different ways. I talked about looking for the signatures of stars moving. And if you track the motions of stars long enough, like we've done in the center of our galaxy or that clouded cluster, you can conclude that there's a black hole there. Another way in which you see black holes in galaxies is through something that Allison works on, AGN. So black holes accrete gas, massive black holes accrete gas, and you can see the glowing gas that's falling into the black holes. And the other thing is that gas can vary with the brightness of that gas can vary over time. So one of the things that the time domain survey will certainly do is see those signatures.
Great. All right, great. Let's thank Dr. Lotz again. So at this point, students, if you have a few minutes and you want to have a chat, stick around. And I will come grab you probably around 12:15.
Okay.
Yeah, yes, you can.